Another topic is planning for HVDC transmission. So where we using HVDC transmission? The planning means where we using HVDC transmission. The system planner must consider DC alternative in transmission expansion. The factors to be considered are cost, technical performance, and reliability. So these factors is considered where we using DC and where we using AC transmission. So while designing the or while erecting the HVDC transmission, you must kept in mind the cost point of view, technical performance, that is a skin effects, corona loss, and third one is reliability. And the reliability point of view, HVDC is better. In technical performance point of view, HVDC is better. In a cost of initial the HVAC is better. Initially means capital cost. Capital cost of AC is very less because there is no converter stations. Whenever there is no converter stations, the filter equipment required is also less. Generally, the last two factors are considered as constraints to be met, and the minimum cost option is selected among various alternatives that meet the specification on technical performance and reliability. For submarine cable transmission and interconnecting two systems of different nominal frequencies, the choice of DC is obvious. In other cases, the choice is to be based on detailed techno-economic comparison. The consideration in the planning for DC depends on the applications. Two applications can be considered as representative. These are long distance bulk power transmission, interconnection between two adjacent systems. In these two factors, HVDC is superior compared to HVAC. The first one is long distance bulk power transmission is very easy by using HVDC transmission. Second one is interconnection between two adjacent system. The interconnection between two adjacent system in AC is difficult because that requires synchronized operation, but the DC does not require any synchronous operations. Synchronous means frequency matching. The frequency matching is required in AC operations. So in these two factors, the DC is very superior. Thus, the choice for DC interconnection will be based on the following considerations. Small fluctuations in the voltage and frequency do not affect the power flow, which can be set at any desired value. So the choice of DC interconnection will be based on the following consideration. First one is small fluctuations. The fluctuations are mainly in AC. The frequency fluctuations are more in AC system. The system security can be enhanced by fast control of DC power. Having settled on the DC link for interconnection, there are three possible configurations for the interconnections. These are A two-terminal transmission where each terminal is located at a suitable place somewhere within the network and connected by a DC overhead line or cable. A back-to-back HVDC station, also called HVDC coupling station, located somewhere within one of the network and an AC line from the other network to the common station. A back-to-back station located close to the border between the two systems. This is special case of the above. So this is a two-terminal DC link. So converter 1, converter 2, in between 2 we using HVDC links. Next one is back to back DC link along with AC feeder. This is a AC feeder. This is a back to back connection. The main application of back to back link connection is to overcome stability problem. If using only AC feeder only, there is a stability problem. If using back to back connection, so there is no matching of frequencies required. This is well suited in HVDC, back to back DC link along with AC feeder. Back to back DC link as border. In borders at the end points of systems, we using the DC link. So then there is no problem of stability. Synchronization is required when we using back to back DC link with in border lines. In border means at the end of stations. At the end of station we using the DC links. The modern trends in DC transmission. To overcome the losses and faults in AC transmission, HVDC transmission is preferred. The trends which are being introduced are for the effective development to reduce the cost of the converters and to improve the performance of the transmission system. Power semiconductor and valves. The IGBTs or GTOs employed required huge amount of current to turn it on, which was a big problem. So in modern trends, the first one is power semiconductor and valves, mainly for in thyristor family, IGBTs and GTOs for employing in converter stations. GTOs are available at 2500 volts and 2100 amps. As the disadvantage of GTOs is the large gate current needed to turn them off. So MCT, which can be switched off by a small current, is preferred as valves. The power rating of thyristor is also increased by better cooling methods. Deionized water cooling has now become a standard and result in reduced losses in cooling. Converter control. The development of microcomputer based converter control equipment has made possible to design system with completely redundant converter control with automatic transfer between system in the case of a problem. The microcomputer based control also has the flexibility to implement adaptive control algorithms or even the use of expert system for fault diagnosis and protection. DC breakers. Parallel rather than series operation of converters is likely as it allows certain flexibility in the planned growth of the system. The DC breaker rating are not likely to exceed the full load rating as the control intervention is expected to limit the fault current. So the DC breaker operation is different from the AC breakers. The cost point of view, DC breakers are very more. Conversion of existing AC lines. There are some operational problems due to electromagnetic induction from AC circuits. where an experimental project of converting a single circuit of a double circuit is under process. Operation with weak AC systems. The strength of AC system connected to the terminals of DC link is measured in terms of short circuit ratio, which is defined as SCR is equal to short circuit level at the converter bus rated DC power. If SCR is less than 3, the AC system is said to be weak system. SCR is less than 3, the AC system is said to be weak. The conventional constant extinction angle control may not be suitable for weak AC system. HVDC converter converts AC to DC and transfer the DC power. Then DC is again converted to AC by using inverter stations. HVDC system mainly consists of two stations. One is in rectifier station and transfer from AC to DC network, and other is inverter station which transfer from DC to AC network. For all HVDC converter, 12 pulse bridge converters are used. This 12 pulse also combining of two 6 pulse bridge converters. Some converter can act as both rectifier as well as an inverter depending upon firing angle alpha. If firing angle alpha less than 90 degrees, the converter acts as in rectifier mode, and if the firing angle alpha is greater than 90 degrees, the converter acts in inverter mode.